So the title of our talk is API Gateway, a Success Story, and I'm Sara.
My name is Carlos, and we both work at System 73. We are a little startup based here in Tenerife. I think that as almost all startup around the world, it began with an idea that was patented. Then we deployed, we developed a application proof of concept that was not production ready, but it helped us to verify the technical viability. And to do so, we developed a set of SDKs for different operating systems, for Android, for iOS, and also for browsers. So to explain what we are talking about, we will try to answer these three questions: why, how, and what. And to give you some little background about to understand these questions, I will try to explain what do we do. We move in the world of the media streaming. So, as an example, if we were streaming this awesome GopherCon event, we would be having a video signal that we would send to the cloud, to a transcoder server, that would generate different resolutions video signals, and with a CDN, a content delivery network, we would launch that signals across the internet to our devices, our laptops, our phone, even our televisions. So System 73, with its product Polynet, what does is to create a distributed content delivery network using the same devices that are watching the video as nodes of a peer-to-peer network to distribute the content and reduce the load of the CDN. When we are talking of live events, the cost must be unexpected, and we try to reduce them. So that client apps that we developed with our SDKs are managed by a backend that implements the patented algorithm. And basically, they see an entry point, a unique entry point that is a load balancer with a set of services behind that manage all that data types. We manage HTTP requests, WebSockets, and different kind of data. So, well, in the way moving from a proof of concept to a production-ready application, we adopted the microservice architecture. So I will try to enumerate, having in mind the previous architecture, what are our requirements to keep moving to the right path. Our main concern was security, because our infrastructure was able to ingest huge amounts of loads. When we talk about live streaming, we can have an event with a few viewers, or we can have an event with thousands, tens of thousands, even millions viewers. So an elaborated attack, if our infrastructure is not able to reject certain requests, may scale up, giving us higher cost, or ever producing a denial of service. We need to improve our data flow because, as you saw, the load balancer has an API stream for each data type. That makes that the infrastructure is highly coupled with the configuration of our application. If we want to put another API stream, we need to change our Terraform code. We need to deploy a new load balancer. So it's much slower than having the infrastructure decoupled from the application configuration. Also, as I said, we need support for HTTP and WebSockets. We need the application to be dynamically configurable. and we need authentication. So we want our clients to be known and get paid for our product and our service. One of the key features we provide with Polynet is the real-time metrics. So latency is key, is a must, because just after some seconds after you play your video, your favorite football match, and you start watching it, we see in our dashboard that you are connected, which bandwidth are you consuming, etc. So at the same time, latency is key for the algorithm, because as we use peer-to-peer connections, we need to have the most recent metrics for nodes to make the proper association between nodes based on certain parameters as the bandwidth and so. Also, scalability is key. As I said, if we have an event with thousands of people connected, almost all people will connect at the beginning. If we are thinking of a football match, everyone will connect at the first time and will disconnect at the end of the match. If we talk about scalability, and as we are using microservices, we need two features to have in mind. Discovery. If I have a microservice and I scale up that microservice, all the rest of the microservices must know of his existence, and load balancing this new microservice, this new instance, must start sharing taking data from all the data that is going inside the system. And last but not least, we would need to implement encryption between the clients and our backend. So, Sara?
Yeah, once we have decided, define all our requirements, we came up to the conclusion that the thing that we need to fill all of this was an API gateway. So why is that? Because as I said, we can fill all the requirements. It is a unique entry point for the system, but this allows us not to implement more logic in each one of the microservices we have, and also not having authentication in each one of them, just in one place. With this feature, we can avoid like non-legit requests early. We can make it high available and scalable, sorry. And it is, we could do it also like container friendly, for example. Also, it is easy configurable, and we can have more things like logging, like request tracing, for example, or application metrics. With an API gateway, we can do just also request manipulation, for example, for checking the authentication or cleaning headers. And you can also cache requests if you have many REST APIs, for example. So how do we put this in our system? We have two solutions in mind. The first one was to explore the already created API gateways in the market. And the second one was to develop our custom API gateway. For the first solution, we were studying three, the most popular, most used, and more complete ones. And we end up with a Kong, Sul, that is the API gateway from Netflix, and the AWS API gateway. Starting with Kong, it has so many advantages. For example, it provides analytics. It is modular, scalable, and also Docker-friendly. You have an admin API in order to store upstreams and manage them. And you also have authentication integrated. The cons about this is that Kong uses like a proxy proxy and a database. In this case, it is Nginx and Postgres to handle upstreams. And Nginx doesn't allow you to manage upstreams dynamically. In order to do so, you have to use a Lua script, which adds latency to our system. And as Carlos said, we cannot allow latency. Sul is a big product that is built by the microservices companies. So if we were using this one, we don't have to worry about maintenance. Like we had less responsibility. It is used in production, so bugs are fixed quickly. The biggest con for our team at the moment was that it is written in Java, and we were not proficient at the moment. So in order to use this, we will need more resources and time, because authentication is done by OAuth, or JSON Web Token, and we needed something like more like API keys. So yeah, and it was so complex to integrate this with our system in order to make a POC. And the last one is the AWS API Gateway. Also the same pros that with the previous one. And the biggest disadvantage is that it's so expensive. As we had so many requests at the time and per second, we cannot allow to pay the cost of this API Gateway. So the last solution available was to make our own API Gateway. If we do this, we can build a specific solution without adding some things that we don't need. The whole team will have control of the system and the service, because everybody is aware of the features, the characteristic, configuration, and also the limitations of the service. And the cool thing is that it could be written in Go. Problems is that we need to test it very well in order to put it into production, because it is a critical service. And also that at the moment we build it, like HTTP client libraries were like immature. So now, having considered the pros and cons of the solutions, the one that we chose was, yes, to build our own API Gateway. We are that crazy. So how do we do this? We chose the language first. Yes, spoiler alert, we use Go. And why did we choose Go? Everybody knows that it's because of Gophers. But also it's very fast, it's concurrency oriented, and it provides cross-platform support. The thing that we did was to make it modular, because as we needed HTTP and WebSocket support, and their scaling needs are different, we thought about making modular so an instance can work over HTTP, over WebSocket, or both modes if you want. I'm saying that scaling needs are different because WebSockets are like established connection. So if you want to scale down a service with WebSocket connections, you cannot do it without closing and reopening the already established connection. We also add authentication, as we said. We use API keys, and we can filter by type because we have many different clients and platforms. We have mobile applications, web browsers, and also TV applications. So this was like a key feature because we can filter requests by type. And also we had a rate limit in order to make the system profitable. It is also easy configurable. I will talk about this later. We call internally the service Cerberus because it is the guard of the underworld gates. And this is how the architecture looks now. We have introduced the API gateway with the security layer with the API keys. About the HTTP proxy, we chose fast HTTP instead of net HTTP because of performance. What we do is that the client makes the request to the API gateway. Then we check the headers, the origin, and we may or not apply the rate limits. And then when everything was fine, the API gateway redirects it's like a proxy path, okay? So it redirects the request to the right service. With the WebSocket, it's the same, but we had to use Gorilla because fast HTTP doesn't have support for WebSocket. We do the same, but in this case, once the request is done to the API gateway and all the checks are done, it upgrades the connection and opens like a double channel, one between the client and the API gateway, and one between the API gateway and the services. This is done using like a double coroutine. I was going to put the code, but it's like hard. About configuration, we wanted to make it simple, and we wanted to make it clean. So we use etcd and YAML files. So this is a simple example of configuration. We only have one instance. It is called API Gateway. And what we have to do is to set the mode to all. Because we want the instance to work either for HTTP and WebSockets, and you set the port of the API gateway. Then we set the upstreams. In this case, we have two, one for HTTP and one for WebSockets. And also, you have to set like the port of the service and the redirection path. Here we have secured to false in order to simplify the example. But you can set it to true, and here are the types of API keys we had, so you can filter at any time.
So Sara has explained so the features that were implemented inside the web service, inside the service, but some of the features that we presented in the first slides were not implemented. Why not? Because we can rely on other services. Our infrastructure is completely deployed in AWS, so we took advantage of one feature of the load balancer that allows you to use a certificate to implement the encryption between clients and the backend, and it's completely transparent to the backend services. You just put your certificate, and connections are encrypted, and it works for HTTPS and also for WebSocket Secure. And on the other side, as our stack is fully Dockerized, we rely on the Docker orchestrator to do the discovery, the service discovery, and we tune the Docker load balancer because the default strategy is to do a round robin. So if you are scaling up and down, it finishes with some services overloaded and other with less charged. So we tune the load balancing strategy, so it makes the difference. But not everything in the development was a walk in the park. We found one of the main headaches we had was with an 502 errors arising between the load balancer and our stack. We have metric endpoints working fine, even with high workloads, almost 30,000 requests per second. We have WebSockets endpoints working fine, but at the API endpoints that had a few requests per second, even less, we're throwing randomly errors. So we start researching, we start looking for documentation, we asked the community. Finally, we were tracing all the Docker networking from the ingest network to the container, inside out. Well, it was many hours invested. So after a few weeks, a few updates on the library, well, finally the errors. We realized that the errors come from the TCP keep alive feature, and in fact, it's a key feature because if you disable the keep alive, the rates you can reach are much lower than with keep alive. So we were crazy for some time, but the rest were fixed. And what did we learn? We learned 1K idea. Bugs arise everywhere, not only in our code, but also in third parties' code. We need to collaborate with the community. Maybe one of the updates in the library was the one that fixed our problem, and maybe was our contribution, or maybe from others, but it's benefit for all of us. And also we learned a lot of Docker networking. Well, talking about performance after the development, when we integrated the service with the rest of the stack, and we do on a regular basis, we do performance tests of the whole stack. We have a simulator that injects traffic, and we get the response times, we get the load of the systems. And so we saw that after putting our new service, everything worked fine. We had the new K features we wanted, and the performance was not highly impacted. Also, during the development phase, we had the idea to know if our service, the service that we were developing, was good enough. So we compared with an Nginx just in the HTTP mode and using Nginx as a proxy, and our service that in fact is a proxy. So fight. Here you can see some of the results. The X signals are for Nginx. These are HTTP response times against the concurrent requests per second. The triangles are our service. It's quite uniform because our service does not have all the features that Nginx is. Obvious, Nginx is a bigger project. It's great. It has a lot of features, but we only do one thing. If we do one thing and we do it right, why? It's faster. And that behavior was also seen in the CPU load of the machine. In most of the cases, the load is similar or lower in our microservices.
So you may be thinking from the beginning of the talk, even now, if we weren't reinventing the wheel, was it worth it? Yes, it was worth it. We had so many great things because of this. We have now a service that fulfills all the requirements we had at the beginning. And in 1 month, we finished the development and started the testing phase, the load phase, and all of this. So in 2 months, we went to production, and everything seemed to work fine. Nothing big broke. So we get some great security improvement in our system, and we were finally production ready. While this was in production, we were adding new features and fixing things. And we ended up with little performance impact in the whole system. We have so many things to improve. That is correct. For example, we can multiplex WebSocket connections, or using custom metrics in order to do load balancing. And the thing we want the most is to make it open source. We cannot make it right now because we add some business logic in order to make it faster and develop it faster too. But I think that with sometimes some plugins, we can make it open source. And we are waiting for your contribution, of course. So thank you. If you have any question about the company, the API gateway, or you just want to talk, just find us.